So really quick, I just wanted a peep game on this for you. This is basically just a microprocessor, and I've got, from the microprocessor, I got my 5 volt and my ground running to the red and blue lines, and I've got a resistor right here connected to my 5 volt, and I've got it pulling up on this voltage, or this temperature sending unit off of an LS1, and then the other side of that sensor is pulled down to ground. And basically this is a voltage divider. So I've got one resistor fighting another resistor, and the voltage between the two will change with the temperature on the sensor. So because of Ohm's law, I can figure out, because I know the value of this is never going to change, but the value of the temperature sensor is always going to change depending on temperature. So using Ohm's law, I can figure out with the voltage I read here what the resistance value is of the sensor. And with the resistance that I measured off of the sensor, I can then calculate the actual temperature. So there's charts all over the internet for it, and I think it's publicly documented on a few GM websites. So what it's going to do is it's going to read the 5 volts on this yellow wire, just so I know exactly that this is whatever voltage close to 5 volts that it's trying to aim at, right, on my 5 volt line. So if there's minor fluctuations in the voltage regulator, it might be 5.01 or 4.99. This just ensures accuracy of the reading. This wire right here is going to read the voltage between my voltage divider, and then I can calculate the resistance of the temp sensor with it. And that voltage is going to be read by pin A1 over here. So, with that being said, if I go over here, and at some point, there we go. So over here, I'm declaring that pin A0 is going to be my voltage input VDD, which is going to be my voltage drop across the pull-up resistor on pin A1. Voltage in, measured voltage, resistance, my pull-up resistor value. I mean, there's just a bunch of different variables here. I've got a correction factor for errors in the actual resistor. The pull-up resistor might not be completely accurate, so the correction factor right here compensates for that. And then this is a bunch of code that I ended up not using anyways. Anyhow, so in my startup, I'm declaring my values as inputs or outputs, and then I've got a serial communication on here so we can actually see what the output is. And then in here, basically, I am reading the voltage input, my 5 volt, and this is going to be a 0 to 1023 value because it's a digital input. It's an analog input on in a digital processor, so it's going to turn into a digital number. It takes the voltage and it scales it to 5 volt. So we know exactly how many volts are on the 5 volt line, whether it's 5.01 or 4.99 or whatever. So it maintains accuracy. Then we measure the voltage in the voltage divider between those two resistors, the temperature sensor and the pull-up resistor. We then calculate it, turn it into a voltage, because this right here is going to read it as a digital 0 to 1023. This voltage measured right here is going to turn it into an actual voltage. Whoa, what did I do here? Yeah, so then we turn that measured voltage into an actual resistance using Ohm's law. And then this is basically just saying that the resistance is below 0. It just equals 0 because you can have negative resistance. And then this right here basically looks up on the temp scale that I defined earlier. Up here I defined my temp scale, which goes all the way up to 344 degrees and goes down as far as, I think, negative 40. And then the resistance scale for the temp sensor is anywhere between 0 ohms and 100,000 ohms, which I don't even read down that far. I think I only go down to like 10K or something. Anyhow, so this is the factory GM scaling, because it's not a straight line. If it was a straight line, I could just use a scale of just, you know, 2 values, but because this is kind of a curve, we have to kind of map it out a little bit. So that's basically what this does. This goes through and finds in the resistance scale, it tries to go through all 27 values and try to find the resistance that's just above it, and then it uses between those two values, the value above it and the value below it, and it scales those. So for example, if I have 0 to 5 volts, I can scale that between the numbers 1 and 10, for example. So if I have 2.5 volts, it'll read 5. It'll come back as a 5. So that's basically what this is doing. This is taking the resistance that's above the resistance it measured and below the resistance it measured, and it's mapping that between the two temperatures between those two resistances to get the actual accurate resistance, or I'm sorry, the temperature for those two resistances. And then it basically takes it and it this is where it scales it. It basically takes the temp output and it maps the resistance scale, and then it looks it up in the temp scale, and then it gives it a temp output, and then it multiplies the temperature output by the temperature correction factor that I had up there earlier, which is like I think 0.98, and then it comes down here and it prints it. So I'm calling serial print, so it'll print the resistance and it'll print the temperature and it'll print how long it takes to compute each time it goes around the loop. So if I come over here, serial monitor, you can see taking 54 milliseconds to cycle each loop, and it's measuring 2900 ohms on the sensor, on the LS1 temp sensor, and that calculates out to be 74 degrees. Just for accuracy's sake, we're in ambient temperature, and I've had the heater on for a while. It's actually kind of hot in here. I need to go turn it down. So we'll go over here, and look at that. It's 74 degrees in the house. How cool is that? Anyways, hope you kind of got an idea of what we're doing over here and how we can, you know, figure this all out. Get some coding done and get these little chips over here to do some work for us. But yeah, hope you understood what I was talking about. Have a nice day, bud.